Hello everyone, I'm Seunghoon Lee from Sungkyunkwan University, and I'm here today to present our paper, ML4RT Priority Assignment Using Machine Learning. Professor Baek from Incheon National University, Professor Hyeongboo from Sungkyunkwan University, Professor Kang Shin from the University of Michigan are co-authors of this work, and Professor Jinkyu Lee from Sungkyunkwan University, who is my advisor, is a corresponding author. We will start by talking about the priority assignment. We'll see of the past studies and our own ways on finding the schedulable priority assignment. In our paper, we explicitly target global fixed priority preemptive as our scheduling algorithm. GFP assigns a fixed priority to each task, where the task can preempt other tasks with relatively lower priority. GFP also holds some challenges as a scheduling algorithm, such as the non-existence of optimal priority assignments when it comes to multiprocessor platforms. It is also impossible to discover every schedulable priority assignment with heuristic priority assignments. Moreover, doing it exhaustively is out of the question since the time complexity is always over n factorial, where n is the number of tasks. What we wanted to do was to make a framework that gets task sets as input and gives schedulable priority assignment as an output. As schedulable, we mean that we can guarantee the target schedulability analysis has no deadline misses. Over many years, various target schedulability analyses have been made, and to categorize them simply, we divided them into two groups. One is OPA-compatible schedulability analysis, where schedulability only depends on a set of its higher priority tasks. These have relatively low performance, and as the naming says, can use OPA to find schedulable priority assignments without exhaustively running through cases. The other group is OPA-incompatible schedulability analysis. They have higher performance than the other group, but since the OPA is not applicable, they have to depend on heuristic priority assignments to meet their goal. So let me clarify this with a simple example. Here we have a task set that consists of 5 tasks, tau 1 through 5. Since the task set only has 5 tasks, it's not an issue to exhaustively go through all 120 cases and find schedulable priority assignments. In such cases, Group B, the OPA-incompatible schedulability analysis, has higher performance than its competitor. But what if the number of tasks grow, such as the case when it's 15 and 15 factorial is around 1.3 trillion? It would be impossible to look for schedulable priority assignments exhaustively. OPA-compatible analyses will not be having any problems since they will be using OPA, which is the same as an exhaustive search. However, the analyses that are not OPA-compatible will be disadvantaged and relying on heuristics. This is a big boohoo for Group B since, first of all, as you have seen in the prior example, it could have done better with an exhaustive search. And secondly, heuristics are selectively choosing priority assignments according to their simple algorithms. We in this paper use machine learning to help out OPA-incompatible schedulability analysis by finding priority assignments that are schedulable but were not selected by the heuristic priority assignments. In the past, there have been studies that have blended machine learning to real-time related topics, such as solving preemptive multitasking without task migrations, applying neural network to a job shop scheduling problem, and so on. But our research is distinctive in ways that we target GFP scheduling and we develop new approaches to the priority assignment using both properties of real-time and machine learning. Now I'll talk about what we did to find schedulable priority assignments. Starting from our PAL framework. PAL framework is an abbreviation for Priority Assignment Learning Framework, which is, as is written right there, a machine learning framework made to discover schedulable priority assignments for GFP. The goal of this framework is to infer a schedulable priority assignment for a task set with n tasks on an n processor platform by training a lot of samples. Let's talk about the structure design of this PAL framework. How can we design the input and output, and which neural architecture among so many should we choose for this framework? Here we have an example task set, which holds 3 tasks tau 1, 2, and 3. And each task have task parameters of t and c, which each are the period and the worst case execution time of the tasks. These 3 tasks become schedulable when the order of schedulable priority assignment is tau 2, tau 1, and tau 3. We focus on making the input and output intuitive. Lists of parameters of each task was used as input, and the order itself was used as output. Selecting the best priority assignments to train was also an issue. There were problems when we trained the neural network with all cases that were schedulable. When three tasks have parameters as such, all 3 factorial cases are schedulable. So let's say we train the neural network with these task sets, and we come up with a test set where only the worst case execution time was doubled for each task. And note that only 2 cases are schedulable for this test set. It would be highly unlikely that the neural network trained like this would only give out our desired answer of 2 schedulable priority assignments. And this is exactly why we need to focus on choosing the right candidates to train. Using system hazard was our first step of selecting the best priority assignment. System hazard is the maximum ratio between the response time and the period for every task. And task set with smaller system hazard is easier to preserve schedulability even when the task parameters change. From here, we will call this case where system hazard becomes the smallest while being no bigger than 1.0 premier priority assignment. If the system hazard were less than 1.0, we would know that this priority assignment was schedulable, and the lesser the value was, the better. Deriving premier priority assignment is crucial by calculating system hazard for every priority assignment, which will be n factorial, is impossible as the number of task sets grow. To be precise, it takes the time complexity of n squared times max ti to calculate the theta, which is the system hazard of a single priority assignment. Trying to derive the premier priority assignment would make us multiply n factorial and therefore becoming intractable as n grows. We had to make an alternative plan that would allow us to mock the results of system hazard while having a lower time complexity. We decided to calculate the system hazards only for the cases chosen by the heuristic priority assignments. This removed the n factorial from the time complexity and replaced it with a variable alpha. Now we have found the less time-consuming way of detecting premier priority assignments. The priority assignments that we will be looking for will be the cases when the system hazard is not bigger than those driven from heuristic priority assignments, which from now on we will call pseudo-premier priority assignments. Pseudo-premier priority assignments, unlike the premier ones, are tractable and will be used actively throughout our framework. For the neural architecture, we will be implementing pointer network made in 2015. We selected this particular neural network since, first of all, its number of input affects the number of output, and also it could infer beyond the maximum length that it has been trained on. Now I'll move on to the implementation. This is the basic sketch of how our PAL framework operates. I'll explain this thoroughly in the later slides. Let's say the base pseudo-premier sample we're holding consists of cases where number of processors is 2 and the number of maximum tasks is 10. In this example, by using these sets, we will show how we generated sets where m is 2 and n is 11. First off, we train the neural network with these samples. Then we get these randomly generated samples with a number of task sets of 11. Thanks to the pointer network, we could infer beyond the maximum length that we have trained the neural network on. When we have tested it through our framework, the framework attaches priority assignments that the neural network estimates to be the most likely for making these assignments schedulable. We should know that since the generation of these samples were random in the first place, we must expect that there are always cases when the task sets are never schedulable. These task sets with priority assignments attached to them again goes through our framework, this time to check if the given priority assignments make the samples pseudo-premier or not. Only the ones that are pseudo-premier are saved as pseudo-premier samples for the case where the number of tasks is 11. We merge these generated pseudo-premier sets into our base sample so that the neural network in turn can be trained with more diverse range of samples. Then again, increment our random generation and the circulation goes on. We generated pseudo-premier samples with only the incrementation of 1 since the results got poorer as the alpha grew. Also, we noticed that adding a small number of pseudo-premier set into the training base set before training enhanced the performance of the framework dramatically, showing more cases of successful guess of the schedulable priority assignments. And the same goes on for the cases where we also increase the number of processors. After we have successfully made this basic PAL, to enhance the generation using machine learning, we tried to generate a small number of pseudo-premier sets, which had one more task than the maximum pseudo-premier samples we have. We ended up deriving inductive properties theoretically. When a pseudo-premier prior assignment has 10 tasks in the order of such, adding a new task, tau 11, while keeping the prior assignment's pseudo-premier was quite simple. We just had to put the new task as the lowest priority while setting the worst case execution time and period according to the equation. This is similar for the cases where we try to make samples that have more processors along with tasks. Since we were using a neural network inside our framework, we had to focus on how to keep the generated samples unbiased and how to make the sample generation faster. Here, unbiased means that task sets that are used for training has different characteristics or patterns in terms of their task parameters, positions, and so on. As I have explained earlier, we have two ways of generating samples: training PAL with smaller size samples and generating them directly, deriving them theoretically. Using the first method is comparatively slow, but if we use unbiased sets for training, the generated sets obviously would not be biased. Meanwhile, theoretical derivation makes samples immediately, but these samples would be highly biased since for every samples made in this way, the task with the smallest priority would have same characteristics. Putting fair amount of these samples inside our base training sample would be disastrous, so even with its benefits of reducing time, we tried using this as less as possible. To be exact, in a ratio of 1 for every 5,000 samples generated by the basic PAL framework. Now, this will be our PAL framework as a whole, where a small amount of pseudo-premier samples made by theoretical derivation are also merged into base samples during the incrementation of number of tasks or number of processors. This increased the performance significantly. For example, if the case where we wanted to generate samples of 4 processors and 18 tasks, what used to take 58 hours to generate 10,000 samples now took only 3 hours. So how did we reduce time for the training data generation process? We tried to find the right number of samples needed for PAL framework to work fairly, and empirically, we ended up generating pseudo-premier samples of 100,000 divided by the number of tasks. So as the number of tasks increased, the amount we had to generate decreased. We also used data augmentation where the tasks were duplicated by changing its position. The meaning of each set is literally the same, but changing the task set's position along with the position of the prior assignment would work as different sets for the neural network, which acknowledges these input and output only as sequence of numbers. Overall, our base samples used for training was kept at this exact number of 500,000 samples generated by training and 100 samples generated by theoretical derivation. We will talk about the sample generation with a simple example. Here we have the case when the number of processors were 2, while we are looking at the scheduled prior assignment holding 9 tasks. We first exhaustively found premier samples as much as possible. For our case, the computation only held till the number of tasks were 8. We found 125,000 premier samples for each number of tasks and made 500,000 premier samples. Then 100 samples made by theoretical derivation, where the number of tasks were 9, was added to enhance the speed of the neural network. Now, these were used to train the neural network. After training, since the target we're looking for has 9 tasks, we generated and found 20,000 samples by machine learning. The other task sets, where the number of tasks were 5 to 8, each decreased their number to 20,000 to keep the ratio inside the base sample. We then merged these to make the total of 100,000 pseudo-premier samples from 5 to 9. We then used data augmentation and quintupled the samples to 500,000. And that was it for successfully making big enough task samples in a decent amount of time. We will now move on to the evaluation. We have evaluated our PAL framework with exhaustive search and DABU. We can see that PAL finds more than 85% of existing schedulable prior assignments when the number of processors and number of task sets are low. Even when the number of processors and tasks increase, it does not lack performance compared to DABU, which is known to have one of the highest performances in this area. We also can see that unlike other methods like ZLL and DABU, PAL shows consistent performance. We also want to point out this blue line where these are the new task sets found schedulable by PAL. PAL can improve GFP schedulability by covering additional GFP schedulable tasks which have been deemed schedulable by none of the existing studies. Also, the schedulability performance of PAL is superior to that of existing studies under many settings. Out of many, we picked 3 to make this chart, which shows how much time was consumed for us to generate, train, and test our PAL framework. It might seem that our sample generation process is quite longer than expected, but if we think of the fact that once trained, it can take any task sets and generate scheduled prior assignments anytime, having a setup take like 2 weeks under a single personal computer seems fair enough. So for our conclusion, we developed the machine learning based framework called PAL. PAL is superior to other methods in many settings. PAL also found schedulable prior assignment that no one has ever found. Although PAL is successful in finding schedulable prior assignment of many tasks with large N, scalability issue is not completely resolved. PAL needs to construct samples incrementally that was around 1 or 2 weeks with a single personal computer. And as the number of tasks increased to be extremely large, PAL struggled on guessing schedulable prior assignments. That's all for my presentation. Thank you all for listening to my talk about our study Elmo for RT priority assignment using machine learning.